3. Yeah? And squared. And the second element would be u hat at time t is 4 squared. And so on. And the last element would be u hat squared at time t, capital T minus 2. So this is basically how our matrix would look like. So our u hat t, which is in this case if we translate it to our OLS simple regression model, and we denote always the left hand side as y. So our y vector would be then simply our u hat just with squared elements. Yeah? So the first element would be obviously the u hat 1 squared. The second element would be u hat 2 squared. The last element would be u hat capital T squared. Yeah. So we define our matrices, yeah, and then we run our OLS model. Let's call it beta b hat is then again x transposed x inverted x transposed y, yeah, using these definitions. So what we get is a parameter vector that gives us now the estimates for delta 0 hat, delta 1 hat, and delta 2 hat. Yeah, this is what we get. So next we get also estimates of our E, yeah? And we know already how we do it. So it's this guy here, our y minus our x times beta hat is our estimated E. And it's a vector, so we don't have to have the time index. So what we need next is we need to determine the R squared. This is a new concept. So what's the R squared in a regression context? So the R squared gives you the part of the explained variation. So it tells you the degree to what extent is your model able to explain the dependent variable. And it's always defined as R square is equal with the estimated or the predicted y. So it's y transposed y hat transposed y hat divided by the actual variation. Yeah? So the actual variation in the dependent variable is defined as y transposed times itself, and the explained variation from the model is the predicted value of the dependent variable, and this is always defined as y hat transposed times y hat. And you can also write it, it's the same, like one can show that 1 minus the error term E transposed E divided by Y transposed Y. Yeah? So that's obviously equivalent, and one can show that. Yeah? So both formulas give the same result for R square. So what we need now is we have to determine the R square from this auxiliary regression. Yeah? And that's why we need all these estimates, so that we can get the estimated E of the error term, because we need it here for the for estimating the R square. So once we have done that, we can easily estimate the R square of that auxiliary regression. Yeah? Let's denote the R square as R square from our vector u hat squared on the legs u hat square minus. Okay, let's just define it like that. So let's take this away now. So important is that you understand that we have this auxiliary regression here, yeah, which have another residual term. It's defined in our case as ET. Yeah, we define our new matrices here, our regressor matrix, the matrix of dependent variables, which is obviously the squared residual from this original regression model. Okay, and then we can get our estimated residual vector of this auxiliary regression, yeah, using this simple formula. Having estimated the residuals of the auxiliary regression, we can easily determine the R squared of that auxiliary regression using this formula here. Yeah? And in this case, obviously, our ET is defined like here, and our Y vector is, in this case, from the auxiliary regression, defined as this guy here, yeah? As our U hat squared. Yeah? These are the elements that we have in our Y vector in the auxiliary regression. This is what you have to bear in mind. So then, let's take this away. So the test statistic, lambda is always used as for denoting a test statistic, is distributed as T times this R square that we have from this auxiliary regression, yeah? Given by regressing the U hat squares on the two legs. Yeah? And if the null hypothesis is true, this test statistic, lambda, is distributed as chi square with 2 degrees of freedom. Why 2 degrees of freedom? Because you remember in the original, auxiliary regression, we had delta 0, delta 1, delta 2. And we had 2 legs. So because we had 2 legs of the squared u's in our auxiliary regression, the test statistic is distributed with 2 degrees of freedom. If we use 5 legs in the auxiliary regression, then this guy would be distributed as chi square with 5 degrees of freedom. So the degrees of freedom depend on how many legs do we have in our auxiliary regression. Yeah? But this formula here is always the same. So T, which is the number of observations in our sample, times the R square of that auxiliary regression. So, and we know from statistics, hopefully, that our chi-square distribution looks something like this. Yeah? That's the chi-square distribution, let's say with 2 degrees of freedom. And I'm now not 100% sure what is the critical value. It could be 5.8 or something. You can look it up in the internet. You will find tables for the chi-square distribution with 2 degrees of freedom. So, but it's obviously a one-tailed distribution, and the critical value is, I don't know, something like 5.8 or so. You can look it up. But whenever our lambda, yeah, exceeds this critical value of the chi-square distribution with 2 degrees of freedom, we reject the null hypothesis. And under the null hypothesis, H0, we assume there is no volatility clustering and in this case obviously we assume that our residuals are well behaving, And the alternative hypothesis H1 is there is volar clustering. Yeah. So again, when our lambda falls into the critical value here, if it's larger than the corresponding critical value or the corresponding value of the 95% probability, here we have 95% probability of the chi-square distribution with 2 degrees of freedom, and whenever this lambda falls in the critical value, when it exceeds this corresponding critical value for the 95% probability, so then we reject the null hypothesis, which means we have obviously significant volatility clustering going on, yeah, which means the variance of ui is unequal with the variance of uj, yeah? Which in turn means we have to use our omega. Yeah? You remember? So when the test statistic falls in this within this 95% probability, so when it is below the critical value here, then of course we can operate with the standard model, where we basically use the sigma square times the identity matrix of dimension t, yeah, for our in implementing our covariance matrix, because in this case we do not reject the null hypothesis, yeah, so we assume that there is no significant volatility clustering going on in our data series. So this is just something that I would like to add here to our discussion. I have not talked about this in earlier courses, but I thought this is maybe an important issue, especially in financial markets, and also in new digital financial markets, in cryptocurrency markets. We have a high level of volatility clustering going on, a high level of uncertainty, and then of course it's very important that we use the correct model in order to implement our covariance matrix of our point estimators, because otherwise we would obviously do wrong inference. Yeah, so let's take this away. In some textbooks, they write, or they argue, if the time series, if the data series is very short, then you can just implement, you can just test the deltas, yeah, with using an f-test. Yeah. But yeah, there are always different ways to implement test statistic. So the topic that I would like to discuss with you next is multiple equation models. Yeah. So, and the methodology is called seemingly unrelated regression. And it's called SUR. So whenever you hear SUR estimator, then obviously this is referred to. So why is this important? So for instance, when we test an asset pricing model, for instance, the Farman-French 3-factor model, or the 5-factor model, or 6-factor model, and we use different test assets. Yeah? We use small stocks, big stocks. We have used portfolios of small stocks, big stocks, and medium stocks. Then obviously we have different test assets on the left-hand side. Yeah? And whereas the regression model on the right-hand side is always the same for all of our test portfolios. Yeah? So in this case, we would like to test the alphas simultaneously. Yeah? We have to do a joint test. And that's where this model comes into play. So let's consider a very simple case, yeah, where we have just two test assets or two independent variables. Okay, so obviously we can use this methodology in different contexts, yeah, not only in finance. So let's define our dependent variable, as we do in this course, always with y, and y can be now the excess return of stock I, of stock 1 at time t. y1t, excess return of the first stock at time t, is equal with alpha 1, which is the regression intercept, plus beta 1 times xt, plus an error term epsilon 1t. So if we have a finance context, yeah, and we want to test the CAPM, obviously, then our xt would be the excess market return at time t, and our beta 1 would measure the exposure of our first stock in excess form against the market factor. And this alpha 1 would measure the part of the return of that stock on the left hand side that is unexplained by the exposure against the market factor. Whereas epsilon is usually assumed to be an error term, yeah, and is typically assumed to be normally distributed with zero mean